great information, okay, that was provided to the round-robin members. Now, any missing information that we did not provide because we didn't have it, information that we didn't know, maybe we don't know the specific composition of the sofa, all these missing information was missing for all the members. And it was the task of each member of each team to come out with a solution for it using fire engineering. That's why we are fire engineers. No? Using decisions and assumptions and looking in the literature and thinking and reconstructing the sofa fire and things like this. This is actually key because this kind of assumptions and missing information is what leads to the results. Prediction levels, well, forget about that. 10 simulations were submitted. 8 of them were field models, 2 of them were zone models. We wanted to have as many simulations as possible and as many different models as possible. Unfortunately, the 8 field models is the same model, guess, and the 2 zone models is the same model, guess. No? So the field model is FDS, and the zone model is CIFAS. So pretty much we all use, without forcing at all everybody used NIST freeware codes. Question, why commercial codes were not involved in this? They were invited, all of them. No? So code developers and users of other codes just didn't participate. That's a question that I leave in the air. Predictions are made in the far field and also, in the field type and also in the zone type. Okay? Because many times we see that in real engineering applications, people use as a field model, but then they interpret the results as a zone model. They take the average of the smoke layer and things like that. Okay, well, let's do that too here, and let's compare the 2 levels. No? Let's see if we can conclude on something. Before, favorite quote that I have, this is very important, because where you are going to see now, we didn't know it before. Okay? So this is what Winston Churchill, somebody says Winston Churchill said, is I always avoid prophesying beforehand, because it is much easier to prophesy after the event has taken place. So in Spain, no, this is like doing, haciendo las quilinas el lunes. You will always know after the match who's going to win. No? It's very easy. So when you think about this, take into account, we didn't know this. Okay? That's why we were brave. Now, results, first set of results. This is the time that you have here, and here's the heat release rate. And each of the colors is each of the models that were provided, each of the 10 models that were provided. You have there those 3 models. You see they are predicting a growth phase. Then they have, the 3 of them have a first post-flashover, and then window was broken. We told them when the window broke because we broke it from outside. And then they have a second flashover phase. That actually they're kind of consistent. They start to diverge between themselves here. More models. Now we are starting to see now there are a few of them are going below it in the growth phase. They're predicting very long growth phase or very fast growth phase. Some of them are predicting, well, most of them here get together because we said when the window was broken. So this point here brings most of the models again together, and then they start to diverge again. But the scatter only grows, okay? And these are what we could almost call the outliers. You will always have 3 of them. Extreme growth phase or very low growth phases. So what we see is a lot of scatter. Heat release rate is the most important variable you want to predict. Not the only one, but it's the most important. The models, each team use a completely different approach to predict this. Some of them prescribe it. They did hand calculations using fire engineering principles, fundamentals, and they said, the heat release rate, I'm not going to predict it. I know which one is it. It's this one. And they went to their model and put it that, prescribed. Some other people said, no, FDS allows me to predict it. I'll just put the ignition source, and I will allow it to burn my solid. Okay? Well, the assumptions lead to this scatter, divergence of the results. You can see below here, this is the time that it was predicted for the flashover. In black is when the flashover took place. Nobody was able to predict flashover. And, I completely forgot about that. What you have here in dots is the experiments. This is very important. We measured the experimental heat release rate inside the compartment using the velocity probes, assuming that all the oxygen that was going in was burning. That's an estimation of the heat release rate, but it's only valid during the post-flashover. So we are not providing results for the growth phase. And you see, heat release rate is not constant in reality. It has variation, but we just wanted an order of magnitude of the value. Okay, it's about 3 megawatts here, and after window break, it's about 5 megawatts. So you see, one of the simulations actually is doing a good job. Okay. Now let's look at the temperature of the smoke layer. So people who were using, teams that were using field models, they have to convert this to zone model. And what you see here now is, these are experiments, and you have a great scatter. most of them under-predicting it. Moreover, the team that did a very good estimation or calculation of the heat release rate, they are not doing that well in the smoke layer. Smoke layer height. No, this is in time where the smoke layer is. It's coming down. The experiments in this case, because the resolution was not as good as in the temperatures, it has a significant error associated with it. You have it here. No, it's this range that you see here. What you see is the models are either predicting very fast growth phase or actually very slow, and the experiments in between, large scatter. We look at the temperatures in the compartment in space. This is what field models are supposed to do, tell you the local temperatures, right? Well, look at that. Over prediction, under prediction, under prediction, over prediction about it, but great scatter, and about it, but with bias towards under prediction. We look at the heat flux at the walls. We have the same. Some of them are over predicting, most of them are under predicting, or actually they're doing better with the wall heat flux than with the temperature of the gas. That's interesting learning. And they're doing better during the post-flash over than during the growth phase. Interesting. We look at the temperature of the wall. We have something like that. Great scatter. Most of them under predicting the temperature, but actually they're doing better in the wall temperature than in the gas phase temperature. Now, we can look at this. Again, we have the same. So what we